In the previous discussion of eels, I mentioned the electric eel. Its ability to discharge electricity is already remarkable enough, reaching as high as 860 volts, which is genuinely astonishing. This raises a bigger question. How did humans go from first recognizing electricity to eventually mastering it? According to the latest research, electric eels are unique to South America. They are mainly distributed in the northeastern part of the continent, especially around the Amazon basin. In body shape and swimming posture, they closely resemble true eels, yet they are not eels at all. True eels belong to the order Anguilliformes within the class Actinopterygii, ray-finned fishes. Electric eels, by contrast, are also ray-finned fishes, but they are closely related to the order Siluriformes, the catfishes. If you ignore the elongated body and look only at the head, both electric eels and catfishes have the same flattened, broad skull that gives them a rather dull appearance. The overall vibe is similar. Apart from the most famous electric eel itself, the other members of this group do not look much like eels. Their bodies are somewhat flattened and taper to a very pointed tail. In English, they are commonly called knife fishes. One of them, the black ghost knifefish, really does look like a blade without a handle. The electric eels proper are represented by 3 species that form a tight little brotherhood. The electric eel, Electrophorus electricus, Volta's electric eel, Electrophorus voltae, and Wagner's electric eel, Electrophorus varii. Most of their relatives produce only weak electric discharges, mere millivolts, used mainly for sensing the environment. Only the 3 electric eel species can generate both weak and strong discharges. The strong ones routinely reach 500-600 volts at 1 to 2 amperes. The record holder, Volta's electric eel, can hit 860 volts. That is extraordinary.
How do they manage such control? Their mastery of electricity has reached an almost supernatural level. The longest individuals can grow to about 2.5 meters, and roughly 80% of that body is devoted to electricity generation. This is what allows them to deliver hundreds of volts and nearly a kilowatt of power with professional-grade efficiency. They generate electricity with 3 specialized organs: the main organ, Sachs's organ, and Hunter's organ. These organs occupy so much space that the rest of the internal organs are squeezed into a small residual cavity. Everything else has to make way for the power plant. Because they often live in turbid water where vision is limited, the Sachs's organ is especially important. It continuously emits a weak 10-volt field that functions like the echolocation of whales and dolphins, allowing the eel to map its surroundings and locate prey. The same electric signals also serve for long-distance communication. Interestingly, lower frequency signals are preferred during courtship. A deeper voice seems to advertise greater strength.
Although broadcasting a low-frequency signal risks revealing one's position to both prey and predators, the ability to do so and still survive is itself a display of power, rather like speaking in a quieter but more authoritative tone during the breeding season. A 2014 study by specialists revealed one of the electric eel's more cunning tactics. It first fires a brief, strong, exploratory discharge. Any nearby hidden prey is either startled into movement or produces a detectable twitch, giving away its location. A follow-up study in 2015 showed that after stunning its prey, the eel often curls its body so that the victim is pressed directly against the positive pole of its electric organs. In normal swimming, the current flows out into the water and returns to the negative pole, with only a fraction passing through the prey. When the eel wraps the victim, most of the current is forced through the prey's body, greatly increasing the damage. This technique is so effective that even a brief bite or light touch can leave an attacker stunned, often before the eel has used its full power. On occasion, an electric eel will even leap partly out of the water to deliver a shock, a behavior that early European explorers in South America quickly learned to respect. The
The eel's own neighbors, the 2-meter-long caimans that share the same habitat, are presumably well aware of the danger. The underlying mechanism is essentially the same process that occurs in ordinary nerve cells. The sodium-potassium pump in the cell membrane uses metabolic energy to create a concentration gradient of sodium and potassium ions, establishing a resting potential of roughly 70 millivolts. When stimulated, ion channels open, the membrane short-circuits, and a rapid discharge occurs. Electric eels simply amplify this principle. Thousands of specialized electrocytes are stacked in series and parallel. By selectively activating small groups of cells, they produce weak sensing fields. By firing the entire battery at once, they generate the high-voltage attack. The eels themselves are protected by insulating tissues that shield their vital organs, so they are largely immune to their own shocks. The result is a near-perfect biological weapon. Electric eels are not unique. Electric catfish, elephant nose fish, and several other lineages have independently evolved electric organs, at least 6 separate times among fishes.
Darwin himself cited these cases as examples of convergent evolution in On the Origin of Species. Ancient Egyptians called the Nile electric catfish the thunderer of the Nile, and the Romans experimented with electric shocks as a form of therapy. Modern scientists continue to draw inspiration from these animals. Researchers have developed hydrogel batteries that mimic the stacked electrocytes, already achieving 110 volts, though only at microampere currents. The long-term goal is soft, biocompatible power sources for wearable or implantable devices. One final biological detail. Despite living in water, electric eels must breathe air. About 80% of their gas exchange occurs at the surface, so they surface every 10-15 minutes to gulp air, much like lungfish. In the dry season, they can survive in tiny remaining pools, which local people sometimes exploit. For the eels, however, the risk of drowning remains real, and their highly specialized electric musculature leaves little room for ordinary swimming power. In short, the electric eel is a living high-voltage system, refined by evolution into one of nature's most elegant and formidable predators.